Hello, good day. Welcome to our week 4 topic. So we have the earth materials, and specifically we will discuss about rocks and minerals. Now, let's go back to the idea of what are rocks and minerals. Now, rocks and minerals are important for learning about earth materials. Aside from that, important also in understanding structure and even systems of the earth. So studying these natural objects incorporates an understanding of earth science, chemistry, physics, and math. And to differentiate the two, rocks are made up of two or more minerals, while we have a mineral, which is a solid material made of one substance that occurs naturally on Earth. And rocks containing valuable minerals, which are called ore. And of course, before discussing in details about rocks and minerals, let's go back to the concept of what specific system, what specific component of the earth include, or what specific sphere of the earth includes the rocks and minerals. And to review, there are four interacting components. We have the geosphere, the atmosphere, the hydrosphere, and the biosphere. And in terms of the importance, we have geosphere comprises the solid earth and includes both earth's surface and the various layers of the earth's interior, while the atmosphere, a gaseous envelope that surrounds the earth and constitutes the transition between its and the vacuum of space. We have also hydrosphere, includes all water on Earth, including the surface water and even the groundwater, while the biosphere is the life zone of the Earth and includes all the living organisms and all organic matter that has not yet decomposed. And specifically, focusing on the solid aspect of the Earth, we have the geosphere. So again, the geosphere is the solid Earth that includes the continental and ocean crust, as well as the various layers of the Earth's interior. And approximately 94% of the Earth is composed of the elements oxygen, silicon, and magnesium. So the geosphere is not static, meaning it's not stable, but its surface is in a constant state of motion. Of course, we have activities. So we have surface activities, the crust activities, that's why it's not static. We have earthquakes. And mineral resources are mined from the geosphere. That's why we need to go back to the concept of the layers of the earth, focusing on what specific sphere, what specific aspect we'll discuss about mineral resources. And going back to the composition and mechanical characteristics, each layer is a distinct layer. So first we have the crust. So the crust consists of 5 to 70 kilometers thick layer of oceanic and continental crust. Of course, composed of 8 elements, namely oxygen, silicon, aluminum, iron, calcium, sodium, potassium, and magnesium. So these are the common elements within our Earth's crust. And divided into two, we have the oceanic and the continental crust. Now, the oceanic crust composed of basal, heavy dark colored, iron-rich rock high in silicon and magnesium. While on the other hand, continental crust comprises the major land masses on Earth that are exposed to the atmosphere. So that's the difference between the oceanic and the continental crust. So very self-explanatory because when we say oceanic crust, it's under the ocean. While if when we say continental crust, it's actually the surface of the Earth, the major land masses on Earth exposed to atmosphere. So here in the illustration, you can really observe, or you can locate where is the continental crust and where is the oceanic crust. So we have also the other layers of the um, Earth right after the crust. Now, we have what we call the Mohorovicic discontinuity, or the MOHO. So this is just above the upper mantle and still part of the crust. Now this Mohorovicic or MOHO, discovered by Croatian seismologist, we have Andrija or Andrija Mohorovic in 1909 while studying seismic waves in an earthquake in Croatia. So the velocity of the seismic waves behave differently as they traveled through this layer before the mantle. That's why it is termed as discontinuity. So that's the definition when we say discontinuity. This is a portion, this is an area where, of course, the component, the structure behaved differently. Then we have also the mantle. So the mantle, it's the layer of the earth below the crust. And of course, the asthenosphere, it lies on the upper part and directly below the crust. So the asthenosphere, this is the extreme temperature, or this is the portion with extreme temperature and pressure, cause the rocks to move, to become ductile and move like liquid. And this is also where the flow of semi-molten rocks in some parts of the brittle crust causes it to break. Some rigid parts of the crust, on the other hand, just float or move about slowly on this liquid-like layer, so supporting the movement of plates as described in the plate tectonics. So that's why there is always a state of motion in the crust portion, and even in the um, area near to the mantle, for the reason that there are structure, like for example the liquid-like layer portion. Of course, this liquid-like layer portion will support the movement of plates. So motion is constant within the crust and even some portion of the mantle. So we have also portion. Now we're in this mantle make up or made up of silicate rocks, meaning most or consistently mantle composed of silicate, and it's the thickest layer of the earth. It holds 84% of the volume of the earth, and most of it is solid, but it behaves like a viscous fluid or a viscous fluid. So the limited knowledge of the scientists have on mantle derived from sinoliths or sinoliths. So these are rocks embedded or trapped in rocks that come straight from a volcano. So sinoliths, the rocks trapped inside the magma, apparently contain most of the primary rocks that originated from the interior of the earth. So hence, these are thought to be the rocks in the mantle. So sinoliths are considered or are thought to be rocks in the mantle. So as I mentioned, that there is also a portion with, or area, a layer with different behavior because of its component. So in the mantle, we have also the Gutenberg discontinuity. So it serves as the transitional boundary between the lower mantle and the outer core. So it's not directly that the component between mantle and core is similar, because in between there is what we call disparity, meaning there is what we call uh, different or with different behavior. There is a transition, meaning it's not like directly its outer core, but there is a portion with different behavior. So that's why we call it as the Gutenberg discontinuity. And it was discovered by Benno Gutenberg in 1913. So the boundary does not remain constant because of changes in the heat flow. So when the heat in the mantle dissipates, so when we say dissipates, that's disappears, the molten core gradually solidifies and shrinks, so moving this boundary deeper and deeper within the Earth's core. So we have here the layers, the discontinuity layers. So we have the Conrod, the Morovicic, the Ripety, the Gutenberg, and we have the Lehmann. So we have for the core. So the core is made up of iron and nickel. And the iron in the outer core is in liquid form, which is why the core is known to be the liquid while the inner core is solid. So even though outer core and inner core composed of iron and nickel, they differ in terms of the state or in terms of its composition. Well, the outer core is liquid while the inner core is solid. So iron is primarily important because this is the primary source of Earth's magnetic field. Now the magnetic field extends outward to protect Earth from solar winds deflecting them. So without magnetic field, the solar winds could damage Earth's atmosphere and all living forms of Earth. Of course, the magnetic field is extremely important to sustaining life on Earth. So without it, we would be exposed to high amounts of radiation from the sun, and our atmosphere would be free to leak into space without the magnetic field. That's why magnetic field is really important portion, really important part of the Earth's concept. And well, of course, we have also the transitional boundary between the inner core and the outer core. So even though that they are composed of iron and nickel, in terms of similarities, they are composed of iron and nickel, but still in between layers, we have what we call transitional boundary or portion, wherein we call it as the Lehmann discontinuity. So it was discovered in 1929 when a large earthquake occurred in New Zealand, and it was discovered by Danish seismologists. So we pronounce it as Inge Lehmann or Inge Lehmann, who studied shock waves and realized that these waves had traveled some distance into the core and then bounced up to some kind of boundary. So with distinct behavior of the waves, it was accepted that there indeed lies a layer that separates the solid inner core from the liquid outer core. Meaning there are differences in between, meaning there is what we call separatory layer between the solid inner core and the liquid outer core. So again, going back to the illustration of the discontinuities. So now, let's proceed to rocks. So rocks, of course, very important. So looking back into the concept of a rock cycle. So just to define, rocks are any solid mass of mineral or mineral-like matter occurring naturally as part of our planet. So rocks are products of a natural cyclic process. So the rock cycle, as I mentioned, an important process. Well, when we say rock cycle, no end, no start. So the rock cycle shows the interrelationship among the three rock types. So we have the igneous, the sedimentary, and the metamorphic. So just to define some terms in relation to the rock cycle, we have magma. So magma is a molten material that forms deep beneath the Earth's surface. So lava is magma that reaches the surface. So weathering is a process in which rocks are broken down by water, air, and living things. So we have also another natural process. We have erosion, which is the process by which soil and rock particles are worn away and moved elsewhere by gravity or by moving transport agent such as wind, water, or ice. And we have also another term, we have sediment, so which is weathered pieces of earth elements. So these are some of the common terms that we will be encountering in the next slides. Now we have classification of rocks as I mentioned in the previous slide. We have igneous, so from the Latin word ignis meaning fire. And igneous rock, of course, I know that you are familiar that igneous rocks formed by the crystallization of molten magma or partially molten volcanic materials that came from within Earth. So in the concept of rock cycle, of course, we have weathering, one of the important processes in the rock cycle. So weathering breaks down the rocks on the surface of the earth. So there are three types of weathering. It could be biological, physical, and we have chemical. So wind and water move the broken rock particles away. So this is what we call erosion. So if you look into the illustration or the cycle, so we have the weathering and erosion. So rivers now and streams transport rock particles to other places. So rock particles are deposited in lakes and seas. So aside from having weathering and erosion, so because of weathering and erosion, some of the rock particles move to other places and it will be deposited there. So like for example in lakes and even in rivers. So from then on, the rock particles form layers. So with compaction and cementation, compaction and cementation presses the layers and sticks the particles together. So this creates sedimentary rock. So again, from metamorphic rock, because of weathering and erosion, or let's have, because when we say a cycle, no start or no ending. So even if we start with igneous rock, so igneous rock, weathering and erosion still, so forming sediment. And then sediments, because of compaction and cementation, it will form sedimentary rock. So even also sedimentary rock will undergo weathering and erosion, forming sediments. So rocks underground get heated and put under pressure and are changed into metamorphic rock. So the sedimentary rock, because of heat and pressure underground, the sedimentary rock will now be or will be converted or will form into metamorphic rock. Or specifically, when we say sedimentary rock to metamorphic rock, it's the change of sedimentary rock to metamorphic rock. So the rocks underground that get heated so much so they melt, so there will be melting, turn into magma, and then the magma also comes from deeper inside the earth, so from a region called the mantle. So the pressure can force magma out of the ground, creating a volcano. And when the magma or the lava cools quickly, it turns into solid, extrusive igneous rock. So when the magma that cools slowly underground forms solid, intrusive igneous rock. So later on we will discuss the differences between extrusive igneous rock and the intrusive igneous rock. But they differ in terms of the cooling capacity, meaning in terms of how the magma cool quickly or slowly. And then areas of rock can move slowly upwards, so pushed up by pressure of the rocks forming underneath. So this is called the uplift. So when there is uplifting, there is also what we call subsidence. So uplifting forming mountains, forming mountain ranges. So that's why we have a higher elevation and we have lower elevation. That's because of the uplifting. So one portion will go up and one portion will go down. Now, as I mentioned, we have the rocks, the differences between extrusive and intrusive. So the extrusive igneous rock, of course, solidifies at surface. So extrusive again. So when the magma or the lava cools quickly, that's the time that an extrusive igneous rock will form. And then when the magma that cools slowly underground, it will form the intrusive igneous rock. So molten magma solidifies through freezing, and intrusive igneous rock, also called as the plutonic rock. So the chemical composition of igneous. So we have examples. We have the felsic, the mafic, the dayanite, and the andesite. Then some common examples of extrusive and intrusive. So we have the basalt, the andesite, and the rhyolite. So with the intrusive, we have the gabbro, the diorite, and we have the granite. So the common granite is an example of intrusive igneous rock. So next we have the sedimentary rock. So sedimentary rocks, from the root word sediments, as I mentioned a while ago, which means remaining particles. So these are particles because of erosion and weathering. So it is formed from the weather products of pre-existing rocks or pieces of dead organisms that have been transported, deposited, compacted, and even cemented. So meaning an igneous rock, a sedimentary rock, and a metamorphic rock will also be or can also be formed sedimentary rocks when their particles will be, or when the sedimentary rocks, the igneous rocks, and the metamorphic rocks eroded and weathered. So the particles formed into sediments and forming sedimentary rocks. So sedimentary rocks show distinct layering or bedding on the surface. Third, we have also the metamorphic rocks. So from the term meta means change and morph means form. So meaning a change in form. So metamorphic rocks are derived from igneous or sedimentary rocks that were exposed to high pressure, high temperature, and a combination of both. So deep below the surface of the earth. So these rocks undergo chemical and physical changes. And metamorphic rocks formed by the alteration of pre-existing rock deep within earth. So, but it is still in the solid state, but because of heat and pressure, or because of the natural activities underneath, then there is what we call the changes in form. There is what we call changes in the formation of rocks, or we call it as metamorphism. Now, we have the examples of metamorphic rocks. We have the schist, the gneiss, and the marble, and even we have the quartzite. Now, in the illustration, you can see here we have what we call high grade and low grade metamorphic rock. Now, how or what factors affecting the grade of metamorphism? So if there is what we call increasing temperature and increasing pressure, it will produce a high grade metamorphic rock. But if the temperature is low and the pressure is low, it will result to a low grade type of what you call metamorphic rock. So high grade metamorphism takes place at temperatures greater than 320 degrees Celsius. So if the temperature greater than 320 degrees Celsius, and of course with relatively high pressure, then it will form a high grade type of metamorphic rock. Next, we have also the minerals. So minerals categorized into groups based on chemical composition. So there, later on in the next slides, we have the criteria before we can consider them as minerals. So elements that combine readily with other elements, they are known to be minerals. So we have silicon, oxygen, and carbon. And the most common mineral groups, we have silicates, oxides, and carbonates. And most common of the classification, we have the silicates. Okay, now there are 5 criteria before we can consider a mineral as a mineral, or before we can say, oh, those are minerals. So first, we have the naturally occurring, or naturally occurring sila. So makikita natin sila sa Earth. Then we have solid substance. Of course, it should be in solid state. And in terms of the crystalline structure, it should be in order. Then we have also definite chemical composition, and of course, generally considered inorganic, not composed of carbon. Now, how minerals are formed? Of course, there are natural processes involved in the formation of minerals. First, we have the crystallization from magma. We have also precipitation, pressure and temperature, and even hydrothermal solutions. So these are common minerals found here on Earth. So some having impurities, some having pure, or we call them as pure minerals. Now minerals, of course, they are distinct and even recognizable because of their characteristics. So we have the common characteristics used in identifying minerals. We have hardness, color, luster, cleavage, tendency to fracture, specific gravity, and shape of crystal. Now let's start with one property. First, we have the hardness. So hardness is a measure of the resistance of a mineral to being scratched. And in determining the hardness of minerals, we are actually using Mohs relative hardness, or the Mohs scale. Now wherein we have the least hard mineral, we have the talc, and we have the hardest mineral, we have the diamond. Of course, hardness refers to the measure of the mineral's resistance to scratching. And as I mentioned, Mohs scale was used to measure, or Mohs scale is used to measure the relative hardness of minerals. Scales from 1 being the softest or the least hard to 10 being the hardest type of mineral. And we have in the table, so going back to the table, the talc, so we have your common powder, baby powder, so they are actually composed of talc, so the mineral talc. And we have the hardest mineral, we have the diamond. Now the main reason why diamond is considered as the hardest, because of the atoms, the composition of the atoms, the formation of the atoms. They are actually compacted compared to the other minerals. Now wherein there is what we call free spaces. So if the atoms are compacted, then it will result to hard mineral. If the atoms having free spaces in between, we of course it's still hard, but least hard compared to the diamond. So here, these are examples of minerals. Next, we have in terms of color. So small amounts of different elements can give the same mineral different colors. However, color considered the least reliable means of identifying minerals for the reason that there are impurities. So, of course, hindi natin magagamit yung color as one of the factor in identifying one of the factors in identifying minerals for the reason that there are impurities sometimes. So in the table below, you can see specific mineral and the mineral color. Alright. Next, another characteristic, we have the luster. So the luster is used to describe how light is reflected from the surface of a mineral. It is how brilliant or dull the mineral is. So this is another characteristic wherein you can easily determine the specific type of mineral by determining how brilliant or how dull it is. Next, we have the cleavage. So the cleavage is the tendency of a mineral to cleave or break along flat and even surfaces. Meaning, may nakikita na siyang area or may portion na dun talagang magkakaroon ng breakage o magkakaroon ng cleave. So, yun yung tawag na cleavage. So, if you are to break a mineral, so the tendency, may portion na doon na kung saan yung area na magbe-break siya. So, we call it as the cleavage. Next, we have the fracture. So, the fracture, these or another characteristic of minerals that do not show cleavage when broken, so which are said to be fracture. And of course, fracture, it is an even breakage of mineral. So kung ang cleavage may specific area siya or specific area of a mineral to break, yung fracture naman wala. So meaning, if you compare the result, yung may cleavage may specific shapes and sizes, while yung fracture naman irregular sizes and irregular shapes ang magagawa niya kasi an even breakage of the mineral. So we have specific gravity. So of course, it is the measurement of the density of a mineral. Then we have also crystal form. So sabi ko nga kanina na one of the criteria, so a criterion in determining a mineral. So we have the crystallization. So crystal form is the visible expression of a mineral's internal arrangement of atoms. Crystal form tells how minerals are arranged. So meaning, crystallization is one of the important characteristics in order to determine, or one of the characteristics for you to determine the specific type of a mineral. Then we have also the transparency or diaphanity. So the diaphanity indicates the extent of light that can pass through the mineral. So very self-explanatory when we say transparency and diaphanity. So transparency, also known as diaphanity, indicating the extent of light passing through the mineral. And then, of course, we have classifications of minerals. We have the mineral groups. So we have number one, the silicate class, which is the largest and the most abundant group, containing silicon and oxygen with some aluminum, magnesium, iron, and calcium. So we have the common examples belonging to this class. We have the feldspar, the pyroxene, the olivine, and we have the quartz. So you can actually search some of the products or some of the products that we have right now composed of the following minerals. Then we have also the carbonate class. So it is mostly found deposited in marine environments. So we have the aragonite, the calcite, and the malachite. So meaning, itong carbonate plus na to, it underwent cementation and compaction of the sediments coming from the like organisms, dead organisms underneath, or dead organisms in the marine environment. So because of compaction and cementation forming these minerals. Then we have the sulfate class, forms in areas with high evaporation rates and where salty waters slowly evaporate. So we have examples. We have the anhydrite, the blue barite, we have the gypsum. So these are examples of the sulfate classes. Next, we have the halide classes. Well, of course, the very common. It contains natural salts. I mean, so relatively low yung hardness. It is transparent and have good cleavage, have low specific gravities, and are poor conductors of heat and electricity. So we have examples of halide class. So we have the halide, the sylvite, and the fluorite. So the fluorite yun yung common sa mga toothpaste nyo. And then we have halide, the common yun sa mga rock salts. And then we have also the oxide class. So the oxide class, these minerals are important as they carry histories of changes in Earth's magnetic field. So the color of minerals in this class range from black to very colorful. So as you can see in the illustration, very colorful. So examples of oxide class, we have the chrysoberyl, and we have the hematite, and we have the spinel. Then we have the sulfide. So the sulfide class considered economically significant. So found in electrical wires, industrial wires, and other things needed in constructions. And of course, some sulfides are mined as sources of such metals such as copper, silver, and lead. And we have also zinc and even tin. So zinc, tin belong to the sulfide class. And then we have the phosphate class. So the phosphate class, considered an important biological mineral found in teeth and bones of many animals. So examples, we have arsenic, phosphate, and vanadium. So phosphates make your teeth hard. So it's phosphate mineral. And then we have native elements. So these are made of nothing but a single element. So contains metals and intermetallic elements such as gold, silver, copper. We have also semi-metals and non-metals. We have for non-metals, we have antimony, bismuth, graphite, and sulfur. Or natural alloys and constituents of few rare meteorites. So recall that a mineral is defined as naturally occurring. Therefore, elements purified and crystallized in a laboratory do not qualify as minerals unless they have also found in nature. So I guess that's the end of our discussion, our week 4 discussion. We have the rocks and minerals. So thank you for listening, and I hope we can discuss more in our synchronous class. So we will discuss, you can ask questions there, about the classification of minerals and other concepts of the rocks and minerals. So thank you very much and have a good day.